Okay, we continue with solving problems on single degree of freedom systems vibrating freely. This one is the problem of the inverted pendulum with frame mass. You might want to check out notes 1 and 2 that contain a brief review of the theory on single degree of freedom systems vibrating freely, as well as some problems on the topic. Okay, so here's the problem statement. Problem number 7. Figure 7.1 shows a uniform rigid frame AOB of distributed mass small m per unit length that is pinned at O and that carries a particle of mass capital M at A. The length of arm OA is small a and that of arm OB is small b. The angle between arms OA and OB is alpha, where alpha is between 0 and 90 degrees. A vertical spring of stiffness K is attached to arm OB. The frame is shown in its static equilibrium position and gravity acts down. What we would like to do is derive the equation of motion of the system for small oscillations. We are going to describe the figures we see here. Figure 7.1 shows the system in its static equilibrium position before motion starts, obviously, where you notice that member OA is shown vertical here. Figure 7.2 is a free body diagram of the system in figure 7.1. Therefore, this is a free body diagram of the system in static equilibrium. We have the weight of the particle at A. We have the weight of member OA, which is MAG. The weight of member OB, which is MBG. Remember that M is a distributed mass per unit length. We have the horizontal and vertical reactions at the pin at O. H and V stand for horizontal and vertical respectively, and S stands for static. And we also have the reaction from the spring on member OB at B that is equal to K delta S, where delta S is the static deflection of the spring. This force, K delta S, is necessary to maintain static equilibrium of the system. Then figure 7.3 is the displaced configuration of the pendulum when the system is set in motion. So when the system starts oscillating, we take a snapshot of the system at any time t, and at that moment of time, the system is frozen in time at a clockwise angle theta here, and here, and also the spring further deflects an amount delta S plus delta, delta static plus some delta, which is the deflection at any time t. And we also define the angle beta, which is the angle made between the vertical member OA and the displaced member OB. Figure 7.4 is the free body diagram of the system when it is set in motion. As before, we have the weight of the particle at A, the weight of member OA, the weight of member OB, the horizontal and vertical reactions at the pin at O, and also the reaction from the spring on member OB at point B, which is now equal to K times delta S plus delta. And finally, we have the inertia term I-O theta double dot acting at point O opposite to the motion. Motion is clockwise by theta. Therefore, I-O theta double dot is counterclockwise at O, because later on we're going to be summing moments about the pin at O. Looking now at figure 7.2, where the system is in static equilibrium, we sum moments about O, and we get the following equation: mg b squared over 2 minus k delta s b equals 0. That's equation 7.1. Again, here delta s is the static deflection of the spring, and we dropped sine alpha from the equation. Next, we set the system in motion, and we sum moments again about point O. This is shown in figure 7.4, and we get the following equation: minus IO theta double dot minus K times delta S plus delta times B sine beta plus MGA sine theta plus MA squared over 2G sine theta plus MB squared over 2G sine beta equals 0. That's equation 7.2. And you notice in this equation that the moment due to the weight of member OB appears in this equation, but as you will see later on, this will be cancelled out. So in this expression, IO is MA squared plus 1/3 small ma cubed plus 1/3 small mb cubed is ma squared plus 1/3 m times a cubed plus b cubed. Obviously this is the mass moment of inertia due to the particle mass, member OA and member OB. And also from the geometry here we get that beta is alpha plus theta, and delta is b times cosine alpha minus cosine beta. Or remember that beta is alpha plus theta, so that gives me b times cosine alpha minus cosine alpha cosine theta plus sine alpha sine theta using a non-trigonometric identity. Also for small theta, we have sine theta is almost equal to theta and cosine theta is almost equal to 1. So using this, we simplify the expression for delta to get delta equals b times theta times sine alpha. Now using the above expressions 7.3 through 7.5 and substituting those into 7.2, we get equation 7.6 right here, which upon again using trigonometric identities 7.6 and rearranging the expression, 7.6 becomes all of this, which is equation 7.7. And you notice in this equation that I grouped the quantities k delta SB minus mb squared over 2g in one term here and also here, and that's because they will cancel out in view of equation 7.1. So now using 7.1 and the fact that small quantities of higher order such as theta squared may be neglected, we finally get to the equation of motion, which reads as ma squared plus 1/3 m times a cubed plus b cubed theta double dot plus kb squared sine squared alpha minus mga minus ma squared over 2g sine alpha times theta equals 0, which is obviously in the form I equivalent theta double dot plus k equivalent theta equals 0. One thing to notice here is that the weight of member OB does not contribute to the equation of motion. It doesn't figure in the equation of motion because it has no contribution to the moment summation, since it is balanced by the static deflection of the spring. It might be insightful to solve this problem using the conservation of energy principle.